Tonight's talk is by John Hebberger Jr. John is the only reason we even have this program. He started this program. It was said it couldn't be done, and he did it. Three of us have replaced John, and we do a third of the talks. And that gives you an idea of the amount of energy and input and creativity that he put into it. John has a master's and bachelor's in geology from the University of Missouri, Columbia. He has personally tutored me in the geology of the area with great patience, and I appreciate it from the bottom of my heart. John is, besides running the Geologists of Jackson Hole, been on the Teton County Library Board, Idaho State University Geosciences Department, Library Foundation, Tax Service, so many other things. I'm going to stop talking and let John talk because it's a fascinating topic. Please welcome John Hebberger.
Okay, good evening, everybody. Thanks for coming, whether you're, I guess, in the virtual world or here in person. This, to me, is an incredibly interesting topic, but I need to warn you before launching into this that there are almost no pictures, just a couple. There's one mathematical formula, and there's a diagram or two. So if words aren't your thing, this is not the talk for you. I'm afraid, other than these two guys up here, I have no pictures of aliens. There's one other later in the program. So let's go ahead and get into this then. And Enrico Fermi posited this question. It wasn't called Fermi's paradox until well after his death, actually, by people who remembered the discussion that he had over lunchtime at Los Alamos in 1950. But he was certainly one of the most brilliant minds of the 20th century. He was instrumental in the Manhattan Project, just a brilliant nuclear physicist, amongst other things. And one of the things he was really famous for was being able to boil really challenging situations, questions down to very short, pithy statements or questions, which is what he did here. And what he posed was simply the question, and this is in 1950, where is everybody? Over a discussion about, is there alien life out there? And, so Teller and a couple of other peers were having this free-thinking discussion over lunchtime, and Fermi posed this question, basically. So let's dive into this then, because 75 years later, we know a whole lot more about the universe than was known back then. It wasn't known that there were any exoplanets. So they assumed at that point in time that there not only were hundreds of billions of stars, but there were hundreds of billions of planets, at least many planets out there, though nobody knew that until we'll talk about that here in just a moment. So the sort of a summary about this presentation then is that you should definitely take away and know that Earth is the only place known to harbor life anywhere. And it is not known, we do not know how life on Earth began, though the rock record makes abundantly clear that it was very, very early. And we certainly know from the things that we think we know about the origins of life, that there were a whole lot of things that had to happen to make life begin, and then to go from single cellular life to complex life, and eventually to what we consider to be intelligent life, though sometimes that's the question. We know absolutely that there are at least 200 to 400 billion stars in this galaxy alone, and there are billions and arguably maybe trillions of galaxies in the universe. So there should be all kinds of planets out there around stars that are similar to our own, in zones. We'll talk about zones a little bit later here that are similar to where Earth sits with respect to its star. Are not. And key questions I think to answer, to address are, how did life begin on Earth? Was it easy, early, and inevitable, or again, or not? And if life is common and inevitable, are the steps to complex life and then the steps to highly intelligent life also common and inevitable? And I guess I should step back sort of the beginning and say there are no answers right now. And I can't give you an answer to Fermi's paradox. In fact, nobody can, though some people will tell you they can, I'm sure. So he posed this question again to Edward Teller and two other genius peers over lunch at Los Alamos. And basically, since, there are so many billions of stars, and even then, before we knew that there were any exoplanets, they were positing that, yes, there probably were lots of them out there. And, if so, probably there's a whole lot of life maybe out there and extraterrestrial civilizations, maybe. But they sort of wandered away from that. And Fermi's sitting there pondering, and he just pops out apparently and says, well, where the hell is everybody? Which got them back into a further discussion about, the possibility of life in the universe and why we don't see it here, at least yet. And I think it's fair to say that 99.99% of scientists on Earth would say that there is zero evidence of this ever having occurred. In other words, evidence appearing here. And I'm sure there's somebody out there who argue with that, but so take, whatever you want, that's okay. Everybody's got opinions, like other things. So the Drake equation was something that was crafted by Frank Drake in 1961 in preparation for one of the very early SETI, or Search for Extraterrestrial Intelligence, meetings. It had, these elements had been talked about before by Fermi and other people as well. But, this is the one formula I'm going to show you. So, and we'll come back to it later. Number of stars in the galaxy, planets, Earth-like ones, fraction in which life emerges, intelligence evolves, technological civilization, ability to communicate, and then the life of that advanced civilization. Those are all the factors there that N equals all those various things. So we'll come back to this later after we've gone through a few other things. So a little bit of background information. The first exoplanet, at least as it is believed, agreed to, was discovered in 1992, orbiting a pulsar star, not a great place to be. But there's well over 6,000 NASA agreed discoveries, and over 8,000 that are right now are candidate discoveries. And it just is going to take more time and more observation to move those to firm planets, discovered planets. We know that there are really hundreds of billions of stars, and the information we have now suggests that there are a lot more planets than there are stars in our galaxy. And again, it's probably trillions of galaxies, not billions, but it's at least hundreds of billions. So, and hundreds of new planets are found with the technology that we have today every year. So, and we are able more and more to actually pull information about, to gather information about these exoplanets. And the technology to do that is advancing, and we're able to determine density. That's relatively easy, but we're even able to tell things about the atmosphere, about some of the planets, exoplanets, nowadays, a little bit. I'm not going to take any questions until the end. There's just too much to go to. So, exoplanet is a planet that is beyond our solar system. Okay. So, and there's enough known about our own solar system, certainly, and our own planet, its geohistory, life on Earth, to begin to really think about the question of life elsewhere, this question that Fermi posed back in 1950. We don't know how life began, but we are absolutely certain that it began very early and then developed very slowly over the 4.56 billion years of Earth history. We see fossils, or very early single-celled fossils going back at least 3.5 billion years. Photosynthesis begins, around 2 billion years ago plus. The major groups of life on Earth, plants, fungi, and animals, appeared about 1.5 billion years ago. Then multicellular, then protozoan, then simple animals, and then half a billion years ago, the Cambrian explosion, which for a long time, back in Darwin's time, was thought to be the beginning of life because they couldn't find at that point fossils earlier. But all the varieties of life that we know today really became evident at the beginning of the Cambrian, that Cambrian explosion. And then almost 4.56 billion years later, you get maybe intelligent life. So we do know that it began early and developed slowly. But one really critical factor that a lot of people don't necessarily think about is we don't know whether life developed on Earth once or more than one time. If it was only once, was it a fluke, an exceedingly rare event, and maybe something unlikely to ever happen anywhere else or ever again? If life developed more than one time on Earth, then statistically, that greatly increases the probability of there being life elsewhere, somewhere else. So the difference between those two scenarios is incredibly important and powerful one. And that's why there's so much interest in, and finally, efforts to try and identify whether there may be other trees of life on Earth if they exist. The problem is that as of today, we only know that there's one tree of life. Every bit of life on this Earth harks back to one, proto-ancestor way back, basically 4 billion years ago. So, if you're able to identify life on another system in our solar system, that would be important, but you would also have to be sure that it's not part of the same tree of life, because things do move back and forth over time between the planets in our solar system here because of impactors that things actually move all the way from Earth when it's hit all the way out to some of the outer planets. That is known. So you would have to not only prove that it's life, but you have to prove that it's a different tree of life. So, if you knew the answer to this question, you would have a much greater ability to, posit that or suggest that there is life elsewhere, I think. You wouldn't prove it, but you would at least, I think, have a better statistical basis for saying that. So what are keys to development of life? Certainly water, early oceans on Earth, and we know now there's pretty good data that suggests that there were oceans on Earth at least 4 billion years ago out of the 4.56 billion years of Earth history. You don't want to be banged around too many times for too long, and the major Earth bombardment ended around 4 billion years ago. Planet has to be big enough. You have to have enough gravity, but not too much, but enough gravity to hold on to atmosphere, water, and to have heat in the interior. You have to have an early atmosphere, and we'll talk a little bit more about that. And you have to have the right kind of atmosphere that allows it to stay warm enough, but not too warm, so it doesn't just freeze up. And you almost certainly, absolutely have to have plate tectonics, and we'll come back to this, but that's what initiated the carbon cycle, and that causes some of the cycling of some of the really important elements that make up our atmosphere and allows life on Earth. We'll come back to that. So you almost certainly have to have a magnetic field, and all the planets in our solar system don't. Venus has a minimal magnetic field. You have to be the right distance out from the sun, which is typically called the Goldilocks zone. You have to be in a place where it's warm enough to have liquid water, but not too warm, like Venus, which the water is all gone. There was probably every bit as much water on Venus, 4 billion years ago as there is on Earth today. You have to have an energy source to create the life. There are organic molecules, we know, not just on Earth. There are organic molecules on meteorites. When we study them, we can see from spectrographs that there are complex organic molecules, throughout the galaxy. And then there are more things, I'm sure, that we have to have because we don't understand all the steps. We don't understand how life began, and we don't even understand, the reason for all the steps that led to more and more and more complex life as life evolved through the 4.56 billion years of Earth history. So we don't know how life began. Then you have the question of, how did complex life begin? Almost certainly the buildup of oxygen in the atmosphere about 2 billion years ago was critical. because oxygen is really important in terms of being able to support energy-hungry life forms like us. You need something called mitochondria, which developed a couple of billion years ago. Power stations, that are found in all complex cells. You almost certainly had to have continents developed, where you then have shallow seas, which would be a much more hospitable environment for the development and evolution of various life forms. Maybe there's a discussion about, we know that there were these global glacial events back in the Archean and Proterozoic, and it might have helped trigger evolution. Almost for sure, the arms race, if you will, between predator and prey is a big factor in terms of helping evolution to move along and develop all the life forms that we know and see on Earth today. And you needed time. We have only one sample, and that's life on Earth. And we know that it started early, but we know that it took an incredible amount of time, all of Earth's history, to evolve us, basically. And other things, and I'll just leave that as, we don't know enough to answer all the questions about not only the origin of life, but its evolution. So it's almost certain that rocky planet is needful. At least most people would agree with that. Not a gas giant. Like, it's hard to believe that you're going to have life develop on Jupiter or Saturn. Moons, maybe, probably not, but maybe. Mercury's too close, it's cooked. So Venus, Earth, and Mars are considered in general to be within what is considered the Goldilocks zone, the zone where surface water on a rocky planet could exist. And we're pretty sure it did exist on all three of these bodies. So this is from a talk by Ken Duker, who is a professor emeritus at the University of Wyoming. And he posited that, well, Earth may be sort of a verdant liquid ocean life-supporting anomaly. Venus lost its water early and greenhoused. It's dry and dead. Mars has lost its atmosphere, and it's cold and windy and dead. There's also a discussion about maybe the lithosphere, in other words, the outer shell of the Earth, how thick it is really important with respect to plate tectonics. Ken posited that Mars is too hard, too thick, the lithosphere. Venus is a little bit too soft. Earth is just right in terms of the lithospheric thickness. And you have water, which very definitely is critical in terms of lubricating plate tectonics on Earth. We'll come back to the Earth being just right in just a moment here. So this is, so it's clearly not just being in the Goldilocks zone, the right distance out from the star, that is important. There are other factors that are very important too. Earth is the only planet, it's the only place anywhere that we know of that has plate tectonics. So, question you may not have thought about is, why does Earth remain habitable over 4.56 billion years, or at least most of that time like that? And the reason, almost for sure, is the carbon cycle. And the carbon cycle does a bunch of things. If you look at that upper left diagram there, it's a very complex set of processes that move materials from the atmosphere to the oceans to the land. And it also acts as a thermostat. In geologic time, the carbon cycle, if the Earth gets a little bit too warm, things change. You can see the steps there, and it cools the Earth. If Earth gets a little bit too cold, and it has been pretty much completely frozen with glaciers if you go back long enough. There are things like volcanoes that put more CO2 in the air and warm the Earth up again. So, but over geologic time, if we're putting too much CO2 in the air, the Earth itself will take care of that, but that's a matter of geologic time, not a matter of mankind kind of lifespan kind of time. But it's even more complex, the carbon cycle, than what I show here. This is just a simplified diagram. It involves other gases and minerals and reactions between them. But a critical part of that, the carbon cycle, is plate tectonics. And we'll look at that here right now. So plate tectonics is a process that more and more, we believe, began over 4 billion years ago on Earth, and has been maybe faster and slower, but has been a constant process through Earth history. And what it does is it cycles things from the atmosphere to minerals, which end up on the seafloor, which end up going down along with oceanic plates underneath the continents, and then stuff comes back up. CO2, carbon dioxide, water, and other gases come back up through volcanism, through the process of volcanism. So that's the cycle. That's part of the cycle then, the carbon cycle, that keeps life on Earth, well, keeps Earth habitable for life. And without the carbon cycle, without plate tectonics, I think I can confidently say that Earth would not be a habitable planet. We would not be here. So Earth's moon could also be very, very critical. There is no other planet, rocky planet like us, that in our solar system that has a moon that is nearly as large as Earth's moon is to the size of the planet that it orbits. It's a pretty accepted theory that the Earth's moon related from a collision by a Mars-sized body, which is typically named Theia, that struck the Earth at a very unique and important angle just after the Earth formed from the materials that were orbiting around our proto-sun, the early sun. And the collision really, I'll explain why, had to be just right. It wasn't a direct impact. It wasn't just a glancing blow. It had to be one that hit at sort of a low angle that caused the metallic elements of the impactor, Theia, to settle into the core of Earth. And then the lighter materials, though, mixed and formed what we consider to be the mantle, the outer part of the Earth today, and also formed the moon. And because of man having visited the moon and brought samples back, we know that the composition of the moon is essentially the same as Earth's outer surfaces, the mantle. And that would not be the case if it was a body, for instance, that was captured by the Earth, an orbiting body that just happened to capture. So, and it's also true that the moon has a very small percentage of its mass, like 1 to 2% is in the metallic core, whereas Earth's mass, about 15% of it is actually in the iron and nickel core. So, those are other pieces of information to, help convince people that this is the kind of collision that had to occur. And so why is it critical? It almost certainly imparted a rapid rotation to the Earth. And that's probably important in terms of the development of a strong magnetic field. Venus does not rotate rapidly and does not have a strong magnetic field. Certainly, the Earth's rotation around its axis over geologic time would likely be chaotic if it didn't have the moon orbiting around it to stabilize its rotation. There would have been giant tides on the Earth early. The moon would have only been about 20,000 miles from the surface of the Earth when it initially created. Today, it's almost 250,000 miles away. So you can get some sense of the tides that would have existed, 4 billion years ago. And not just in the oceans either, but in the rock as well, the rock surface of the Earth. And again, it almost certainly caused a larger metallic core to be part of what is Earth today that we know it. And therefore, a powerful magnetic field that protects the surface of the Earth from radiation from the sun and from the universe beyond. It very likely enabled plate tectonics to occur as well, possibly because of a thinner crust and a hotter interior. And more conjecturally, maybe it had something to do with the early atmosphere, and maybe it wouldn't have been so good if you hadn't had this impactor. So, what do the rocky planets tell us about the solar system? Plate tectonics is likely critical. It recycles elements in geologic time continuously throughout Earth's history. Life itself really, truly helps to make the planet suitable for life itself. Without the development of oxygen-rich atmosphere that began weakly, but began 2.5 billion years ago, you might maybe still have a very thick methane-rich atmosphere, which would be that's a hellacious greenhouse gas, and it would be too hot. So the moon is almost certainly critical, and again, the situation that caused it to happen is very arguably a very rare kind of situation. So, again, it resulted almost arguably in a magnetic field and a rapid rotation, unlike Venus today. Single cellular life began early, but complex life, took basically all of Earth's history here to happen, to begin. So what does this suggest about life elsewhere? And now I'd like to move out into the galaxy, if you will. The discovery of the first exoplanet, again, as I mentioned early, though there was talk about exoplanets for centuries. The first one was discovered in 1992, orbiting a pulsar star, so a dead star, not a great place to be. The first really, a sun-like star with planets orbiting it was discovered in 1995. And this really, begins the era of exoplanet discoveries, of which now we're up to over 6,000 exoplanets that are known to exist. So again, NASA lists over 6,000, over 8,000 candidates, and we're finding several hundred every year. And we're at a point now where we know enough about stars elsewhere in the galaxy and the planets around them that there are probably, almost certainly, a good many more planets than the 200 to 400 billion stars that make up the Milky Way. So something else that's critical, then, I touched on this, the Goldilocks zone, is the distance that planets orbit a star is absolutely critical. We just cannot, the only kind of life we can conceive is our own, and certainly any life that we know of requires water. And you have to be the right distance from a given star, to be in a situation where you're not too hot and you're not too cold. And you can see that depending on the size and mass of the star, you have to be further out, and less mass and you're further in. And our sun is a G-type star. And here's a little chart that shows those various star classes there and the solar masses that they represent. But it's not just the distance, though, out from the star that is critical. The star itself is really critical for several reasons. The smaller a star is, the longer its life. So really giant stars don't last very long. We know that life took a long time to really develop in a significant way on Earth, even though it began early. And if you look at the bigger stars, you see they don't last very long. Their hydrogen fuel burns up really, really quickly. Our star likely has a life in its main sequence phase of about 10 billion years. But even that is probably more time than life is going to have on this Earth. We're at 4.56, 500 million years from now. The sun, I said that, I think, earlier, maybe, where is it? Our sun, when Earth began, was only about 70% as bright as it is today. And it's been increasing in brightness and energy output throughout its history. So where we're at today, so Venus might have been a great place to be, when life began on Earth. It could have been oceans, probably were oceans there. The sun has gotten brighter ever since. And it's going to continue to get brighter and put out more energy. And that means that Earth won't continue to be a really great place to be if you stick around for a couple of hundred, say 400 or 500 million more years, which in geologic time isn't all that long. So maybe some of the smaller stars are actually a better bet than the K-class stars, which aren't that much smaller than Earth and still would have expected life of something like 50 billion years. And what about the red dwarfs, the M-class stars, which actually some of them, smaller ones, would have a life measured in trillions of years. And those are the most abundant star in the galaxy. There's like 70 to 75% of the stars in the galaxy are M-class red dwarfs. There's a problem, or a couple of problems with them, though, and that is that the habitable zone, the Goldilocks zone, is pretty close in, and an orbiting planet would end up being tidally locked, just like the moon is to the Earth. In other words, we only see one face of the moon as it orbits. So it makes an orbit, spins on its axis once in its orbit around the Earth. And that would be the situation with a planet that is close enough to be in the Goldilocks zone of a M-class or red dwarf star. They're also very active, putting out a lot of flares and things like that, radiation, which would be rather detrimental to possible life. So it's possible that maybe what you need to look for is only G and K type stars, though there's not absolute agreement on that. But G and K type stars, our sun and the slightly smaller ones, only make up about 20% of the stars in our galaxy. And again, the M-class red dwarfs make up about 70 to 75%. So
move the cursor from the top. Just drag it down because it's
you do it.
It's bringing up that.
Okay. I didn't do that.
No.
All right. Distance from the galactic center is probably also very important. It seems that the further out you are from the galactic center, the stars and probably the planets around them tend to have fewer of the heavier elements, though there's a little bit of discussion and argument about that. So closer in may be better, but you cannot be too close in. The center of our galaxy is an incredibly energetic place. You would be, if you were very far in, you would be orbiting a massive black hole that is putting out incredible amounts of energy at various times. Also, if you're in a place where there are lots and lots and lots of stars nearby, if a star goes into a nova phase, it puts out an incredible amount of radiation that would be very inhospitable for life. So you don't want to be where there's too many stars. You certainly don't want to be right next to the black hole in the center. And there's even been discussion at various points. People have posited that some of the extinction events on Earth might have been caused by novas occurring, supernovas occurring in stars that bathe the Earth in enough radiation to have an impact on life on Earth. But that's something that is still a matter of exploration and discovery to be. It's not, we don't know for sure. So, there's argument that maybe the galactic habitable zone, the GHZ, you got to be maybe something like 25,000 light years out from the center. And maybe it's, it's expanding zone. Maybe you don't want to be too far out. And you probably want to have older stars. The Earth 4 billion years ago, we wouldn't have recognized much in the way of life on it. So that distance in a galaxy is also arguably very, very important. So, how would you know that there is life beyond the solar system? If you could identify, and we're starting to see bits of data about the atmospheres of exoplanets. But if you identified unstable gases in the atmosphere of an exoplanet, methane, O2, O3, ozone, nitrogen oxide, those are not stable geologically speaking. So if you found those, you would have evidence that maybe there is life on that planet. There are other ways to derive those gases, but if there was a lot of it, it would be telling. It would be a strong clue. Water, if you could identify that there's water on the surface of the exoplanet, that would be something that would be very important in terms of the possibility of life. Again, if we think based on our one sample, without water, there is no life. So water is one of the keys that you have to find. If you found chlorophyll, there's speculation that other life, if it developed elsewhere, would develop something similar to or the same as chlorophyll as it developed here on Earth. And you might be able to develop or detect that by spectrography. And if we look at some spectrographs here of Venus, Earth, and Mars, while we can't really do this for Earth-sized planets around other stars yet, we're not far away from being able to do so. You can see that when you look at the spectrograph of Earth, you see evidence for water and ozone and methane, whereas if you look at the spectrographs for Venus and Mars, our dead sister planets, if you will, those don't exist. So if you saw a spectrograph that looked like Earth's spectrograph, that would be a very powerful clue that life exists somewhere else on another exoplanet. So, what would constitute absolute definitive proof that there is life, beyond the solar system? And certainly SETI, is Search for Extraterrestrial Intelligence, is attempting to do that, monitoring the electromagnetic spectrum for signals from somebody else somewhere else. Or ET visits Earth. And of course, obviously, it's been proven by a movie that it happened at least once. So, I guess we've all seen ET at one point in our pasts here. So let's come back to the Fermi paradox then, and his question about if there's all these planets out there, and they didn't even know that, then where is everybody? Earth is, by galactic standards, young. There are billions of planets out there that are much older, and they might have had more time to develop life on them. It's taken all of Earth's history to develop what we consider to be intelligent life on Earth. The universe is over 13 billion years old, so arguably there's been a lot of time for intelligent life to form and spread. And if not life itself, we send probes out through our solar system, and it's quite conceivable that an intelligent, more technically advanced civilization than us would be able to send machines probes out that would span potentially the galaxy. The galaxy is only a mere 100,000 light years in diameter, and in the scope of the universe, that's not very much, really. So, there are lots of hypotheses as to why we don't see evidence for intelligent life. And some people take that lack of data to say that there is no other intelligent life. Carl Sagan turned that on his head, saying that lack of evidence is not the evidence for lack of life elsewhere. He was certainly a true believer, I think, without a doubt. So those probes are typically called von Neumann machines, and John von Neumann was another brilliant mind of the 20th century, and he is somebody who posited very early on that self-replicating machines are something that are probably in the future. And it's certainly conceivable, given how much our technology has changed in the last century alone. We can certainly conceive of the possibility of us being able to create machines that would be self-replicating and then make space probes that could self-replicate after reaching another world. We also there's people talking about using space sails to reach, a significant percentage of the speed of light. 10% is very rational, reasonable from a technological perspective. And the Milky Way is, only 100,000 light years across. So if a civilization sent out von Neumann machines, which self-replicated and then spread further, it's very conceivable that they could have spread across our galaxy in a mere few million years, which in the scope of Earth's history is, it's almost no time at all. So, many people think, I tend to think so too, if mankind, human civilization gets to a point where we could do that, I think we would. We would send out probes to explore beyond just our own solar system like this. The point, though, you have to remember is there is zero evidence for something like this ever having reached Earth, as far as anybody, I think, can reasonably show. So let's come back to the Drake equation then here and look at these, these factors in the Drake equation. I'm not going to go through all these, but we do now know certainly the number of stars in our galaxy pretty accurately. We have a pretty good idea now, based on the last 30 years of research of gathering data, that there's a lot of planets out there. So that's a pretty reasonable number. How many are Earth-like? That's getting to a point where we really don't have very good data yet, but there are out there for sure. How about ones that life emerges, ones that intelligence evolves? How about ones that they are a technological civilization that could communicate across the galaxy? And how long might a civilization like that last? The key point is that if any of these values are zero, the answer to n is zero. So I don't know what the answer is. But as we'll see in just a moment, there are guesses from 0 to a whole lot. And I say, remember Earth and Venus, you can't just be in the Goldilocks zone. There are a lot of other things that are critical in terms of the development of life, at least on Earth. So many of these variables are unknown. Again, any factor that is 0 means the answer is 0. And estimates vary from they're everywhere to, there aren't any others. It really just depends on how you interpret the data that we have to this point. And, that database is growing, on a, I don't know if daily, but certainly on a monthly basis in terms of information about exoplanets that are out there, the number, and things about their atmosphere, and more advanced tools are in the planning stage right now that would allow us to even do a much better job of evaluating exoplanets, planets around stars, light years away from here. So in summary, this is the only place known to have life, Earth. We don't know how it began, though we do know that it began very, very early in Earth's history. Earth was habitable very, very early. As best we know to this point, there's only one tree of life. There's only evidence that it began once on Earth so far. We do know, that there are hundreds of billions of stars and certainly hundreds of billions of planets out there. And there are billions, if not trillions, of galaxies. So there should be many planets orbiting stars, ones like our own, G or K class stars, that would be in the habitable zone. In other words, about the same distance out as Earth is from our sun, so that you have conditions suitable for water on the surface of that planet. And the building blocks of life, complex organic molecules, appear to be very common, not just within our solar system. We see evidence of that, but also, out in the galaxy, in interstellar gases, and almost certainly then in the planets that orbit those stars that are out there making up the galaxy. So, is life inevitable? Is it common? We have an increasing understanding of early Earth and the many things that had to happen to make complex life able to develop, though all those steps we don't understand yet. So key questions might be, how did life begin on Earth? We don't know yet. Was it easy, early, and inevitable? We don't know. If life is common and inevitable, beyond that are the steps to complex life and then intelligent life inevitable. Again, it took basically all of Earth's history to reach us. So, going back to Fermi's question, given that there's 13 plus billion years of, time in our universe, where is everybody? So, and no one has the answer. And I'm not going to put numbers on the Drake equation. They're like that. But I will argue that this is an exciting time to be alive. Think how much has changed just in the last century. Just 30 years ago, we did not know that planets existed beyond our own solar system. So much has changed. And we're now being able to actually gather information about some of those planets, those exoplanets, light years away from Earth. So we have the chance to be alive when we have a much, much clearer answer, to this question. And certainly I think our children and grandchildren certainly will or do. So, I'll leave you with this question. What do you think the likelihood of life and then intelligent life is beyond Earth? And I'll give you, some suggested readings here. This is being recorded, I think, so you could look at all of these suggested possible readings. I might suggest that Rare Earth, if you really want to dig into this, would be a good place. It's one of the oldest books about discussing, whether there is life elsewhere or not. Wikipedia has a lot of good information. And you can see that there are things like Life Everywhere by David Darling. There are people that are very certain that there is life elsewhere. If you really want to read somebody who today is in the news and is absolutely certain that life is everywhere and has actually maybe even visited us, then read some of Avi Loeb's. He's a professor at Harvard. Read his book Interstellar, which is a very new one. Or you also might want to read one of those other ones, the bottom two down there, Alone in the Universe. If the universe is teeming, where is everybody? So I just want to say thanks for your attention. That's what I've got. And if anybody has questions at this point, I'd be willing to entertain them. But I have no absolute answer. Get light on. So, Arna.
Your definition of love.
That's my
Ooh.
I don't know. It's sort of like pornography. I'll know it when I see it. There are definitions. There are things that, self-replicating bodies that use energy, is sort of a real basic, I think, definition. And there are things that self-replicate. Minerals can, for instance. So you get into a bit of a gray zone, but a self-replicating body that evolves, I think, also probably is a reasonable. It's probably about as good as I can offer you.
So can you touch on the idea that our sun is a probably third generation sun, and early stars would not have created the elements that are necessary for life. And so that 13 billion years is probably a smaller number because you had to have stellar evolution and the production of carbon and nitrogen and these other elements that didn't happen in the early universe.
Well, the question was, I should repeat the first one, what was life? That was what Arna asked. And Mike sure just asked, early on, there was only hydrogen, helium, and a tiny bit of lithium, at the Big Bang. And, it took a while, various stellar cycles to begin to generate heavier elements. But there's growing evidence that pretty early, there's a lot of the heavier elements. So yeah, there's more of the metallic elements. We see everything beyond hydrogen and helium. The first stars had only hydrogen and helium, but there probably was quite a bit fairly early. Because you went through a lot of stellar evolution pretty early. Remember, the big stars, the giant stars, only last, a million to tens of millions of years. So they're doing their thing. They're going nova, stellar, supernovas and generating heavy elements. You probably had black holes very early. They collide, or neutron stars collide and create heavier elements. So there's probably more. It's probably not as much of an issue as people maybe thought early. That there weren't enough heavy elements early. There probably were, not as much as today. I mean, you're continually generating a greater percentage of heavy elements as the universe, as our galaxy, as stars evolve. But it probably is not as big of a deal as some people thought earlier, I think.
So didn't Carl Sagan suggest that our definition of life was too narrow, and that maybe there's life out there, but we can't recognize it?
The question was, didn't Carl Sagan suggest that there's a lot more different types of life than we recognize, and maybe we wouldn't be able to recognize that type of life. There's been discussion about life using silicon as a basis as opposed to carbon. Carbon is a basis for life as we know it. There are chemical processes that can occur based on silica, but there's nothing that is as suitable for the types of chemical processes that occur that we recognize that are as likely to produce life as carbon-based processes. So the organic molecules that we talk about are all carbon-based molecules. And maybe it could happen. You saw it on Star Trek. They chased the little silicon guys around in the caves or whatnot. I remember that when I was growing up. But I think most people would posit that you have to have water, you have to have carbon to form life. And so we probably would recognize it, despite Carl Sagan's thoughts to the contrary. He was a true believer, that for sure. I mean, Carl Sagan certainly was a true believer that life is out there.
Here's about like Saturn's moon, Titan, for example, liquid methane, oceans, kind of following up with this previous question of the possibility of life exists outside of a Goldilocks zone in another liquid system that's not water.
So the question is, how about life developing in the moons of the outer planets, Saturn and Jupiter, and maybe in methane, like on Titan, is it? That has the oceans of methane on it. Maybe. We don't know enough to say yes or no. But you got to remember too that those methane oceans are about 200 degrees below zero. That's what it takes to get liquid methane. Do you have all kinds of other elements that would make life possible? I don't think we know. There's discussion about probes going to Titan to go down into those methane oceans, or actually land on the continents between the methane oceans and see if there's evidence for complex life, I guess. But that question is, I guess the answer to that is way beyond my pay grade. So maybe, but the life that we know, the one sample that we have, requires things that don't fit with that kind of environment. Is it possible? I don't know. What are my thoughts on Comet 31 Atlas? I suggest that you read Avi Loeb's spread across the internet right now, his discussion about that one and about Oumuamua, which is the first interstellar object that we know that came through the solar system here. And he posited that it was actually a machine. I think Avi Loeb is way beyond Carl Sagan in terms of being a true believer, that life is out there, intelligent life is out there. And for me, he's too extreme. I think it's an interstellar comet that's gone through, and I think the data that NASA has gathered and published, there's a very non-intelligent life explanation for all the aspects of the things that have come from interstellar space that we've seen so far. And certainly, unlike the movie, E.T. hasn't landed and blowing the kids around on their bikes and all that kind of stuff. So there just is, in my estimation, I think most people's serious scientists' estimation, Avi Loeb is a very brilliant scientist. Most people would posit that we have not seen any evidence yet in any form of intelligent life or any life elsewhere beyond Earth.
You mentioned the self-replicating machines, Neumann machines.
Von Neumann machines, yep.
theory on how to self-replicate?
Well, we haven't made any. Yeah. So the question was von Neumann machines and what's the theory behind how they would self-replicate. We haven't made any yet. There is serious discussion about what it might take. We do have machines that print pieces of other machines. So it would be some kind of combination of a very intelligent AI-based computer with a machine that could self-replicate, could print, could go. So for instance, there's been serious discussion about what would it take to live on the moon. And there's been serious discussion about we need to put machines up there that can use solar or lunar regolith, break the elements down and print other kinds of machines. It's a step beyond to say you replicate basically another AI intelligent computer, but it's not, I think, beyond the realm. When you think how far we've come in a century here, a little over a century, there was no such thing as flight. There was no such thing as computers. There was no such thing as atom bombs, nuclear power. 30 years ago, we didn't know that planets existed. And let's see, the Hubble Space Telescope went up in 1980, something like that. I've forgotten exactly when. The technology, the pace of technological evolution is such, in my estimation, that certainly a century from now, and I won't be around to, you can't test me on this, I would have to guess that well within a century, we would have the technological skill and ability, if we don't destroy ourselves, to create something just like that. And there already is discussion about sending out solar light sail dragged little bitty tiny machines that would go to other stars and send back a signal saying what's there, maybe. So I don't know. Anybody else? Anybody else want to take a shot? Does anybody else think there's life out there? A lot of people do. I don't know. That's it is. I'll also say, though, that I'll sort of wrap this up by saying we continue to get more and more information, better information all the time. And I think the longer we go and gather more information and don't see evidence of life elsewhere, the probability of life elsewhere, and in particular intelligent life, I think has to be seen to decrease. The probability has to get lower. But there are a lot of people in a lot of these books that I offered you as possible reads, talk about why life has to be everywhere else. But then some of the other, things that you can read, pose very pertinent questions around Fermi's paradox. Where is everybody? There's a whole lot of discussion about that, and there's a lot of great stuff out there if you want to dive and get lost for a week or three in the discussion about this question about life elsewhere. Last question, Arne.
Okay, so the proposed satellite that we sent to the star, how big is that? And what are the chances that anyone in that solar system would be able to identify?
So the question Arne posed is, what would we create? How big would it be? What kind of probes would we send out? What kind of von Neumann machines? I don't know. Come back in 50, 20, 40, 50 years, and maybe there'll be an answer. And would somebody, an intelligent life in this other stellar system on another planet be able to recognize it as something from another civilization? I think the answer is yes. If a machine landed here that we knew we hadn't made, if you believe in UFOs, maybe they're already here. I think we would recognize that it's something that we have not made, that we're not capable of making. Well, yeah, I mean, it could be something incredibly tiny, maybe. The discussion about, and there was a proposal, and a Russian billionaire was going to fund it, and that's gone away, but he was going to fund actually creating stellar solar sails with chip size sensors being dragged behind it. And that's probably about the level of technology that we're at right now. That would be barely possible. But 20, 40, 50, 100 years from now, I don't, when you look back at how technology has advanced here on our own planet Earth and our own civilization, I think it's pretty hard to imagine what things might look like in that kind of time frame.